In question 1, we're asked if f of x is continuous at x equal 2, and if it's not continuous, state why and determine if the discontinuity is removable. Okay, let's look at this first part A. And we have f of x is equal to x squared minus 4 over x minus 2. It's a rational function. We can't substitute in 2 to take the limit because the denominator is 0 at 2. So f of x actually does not exist at x equal 2 because of the x minus 2 in the denominator. So because of that, f is not continuous at x equal 2. If you recall, what does it take for a function to be discontinuous? Let's write it down, or for a function to be continuous. Let's just write it down over here. F of x continuous if, and there are 3 conditions. The first one is f of 2 exists. Or in other words, 2 is in the domain, and in this case 2 is not in the domain because of that x minus 2 in the denominator. The second condition is the limit as x goes to 2 of f of x exists. And the third is that this limit is equal to the value f of 2. Okay, so that these are both, so this and this must be the same. Okay, so we determined that A is not continuous, f not continuous, since f of 2 does not exist. Now, in order for the discontinuity x equal 2 to be removable, this limit must exist. So let's try to take the limit and see if the limit exists. So let's do that. I'm going to write x squared minus 4 as x minus 2x plus 2. And we have one of our limit laws says that if we have a rational function which is 0, which is 0 in the numerator and 0 in the denominator as x approaches c, okay, let's say x approaches c, in this case 2, if we plug in 2 into the numerator and denominator, if we get 0 over 0, if we can reduce this rational expression like we can here, we have a 0 over 0, if we have a 0 over 0 expression and we can reduce it, and if upon reducing or after reducing the function is no longer 0 in the numerator and denominator, then we can simply substitute in x equal 2. So that's the case here. Once we reduce, we have a quotient of x plus 2 over 1. So we got rid of the 0 over 0 situation, so now we can just substitute in x equal 2. So let's do that. When we get 2 plus 2, we have a limit of 4. So this is the limit. The limit does exist. F of 2 doesn't exist, but the limit as x goes to 2 does exist. So since this limit exists, okay, and we already established that the function is discontinuous at x equal 2, but the limit does exist. That means that the discontinuity is removable. Okay, in choice B, we have a piecewise defined function. For x less than 2, f of x is 2x plus 3. For x greater than or equal to 2, f of x is x plus 5. Now, we want to know if the function is continuous at x equal 2. Well, a quick way of determining this, or a quick way of seeing this, is first of all to substitute in 2 into the numerator and denominator. Okay, if we do that, in the numerator we have 2 plus 2, that's 4, plus 3 is 7, and in the sorry, not numerator and denominator, but in the top function we have 7 when we substitute in 2, and in the bottom function we have 2 plus 5, which is 7 as well. So from a quick glance we can determine that this is continuous, because these are two linear functions and they do meet up at x equal 2. At x equal 2 they meet at the point 2 comma 7. But that is not a proof that f of x is continuous at x equal 2. Now, that's not the formal way of showing that f of x is continuous at x equal 2. That's just a quick way of seeing it. Let's formally show that f of x is in fact continuous at x equal 2. Well, first we have to explain that f of 2 does exist. F of 2, that's condition 1 here. We want to show that f of 2 exists. F of 2 is equal to, okay, we use this line, this function, to determine f of 2, because here it says x greater than or equal to 2. Substitute 2 into here and we get 7. So f of 2 is equal to 2 plus 5, which is 7. So f of 2 exists. Now let's look at the limit. Well, when we have a piecewise defined function, we have to take the limit in 2 steps, to the left and the right. So first, for x less than 2, the limit as x goes to 2. From the left, from values less than 2. Okay, so we use the top expression. That's what we use to determine values of f if x is less than 2. So the limit as x goes to 2 from the left is equal to, now just substitute in to actually take the limit. 2 times 2 is 4 plus 3, that's 7. And the limit as x goes to 2 from values bigger than 2 from the right we use the second line. Okay, x greater than or equal to 2 represents values to the right of 2. Okay, so when we take the limit, we simply substitute in. Okay, so since the limit from the left is equal to the limit from the right, that means the limit exists and it's equal to that shared value. So that we write it like this. The limit as x goes to 2 from the left of f is equal to the limit as x goes to 2 from the right of f. Okay, so that implies that the limit as x goes to 2 of f is equal to that shared value of 7. Okay, so then we did show all 3 conditions. First condition, f of 2 exists. Second condition, the limit as x goes to 2 exists. Third condition, this limit is actually equal to f of 2. Here's the limit. Here's f of 2. So the 3 conditions hold, so we say f continuous at x equal 2. Okay, so let's look at part C. We have another piecewise defined function. Let's find that. It's right here. Okay, so we have x minus 3, 2x plus 5. Let me rewrite it. And let me just take another glance here. This one is x less than 2, x greater than or equal to 2. So here we have x less than 2, x greater than or equal to 2. Okay. Again, quick glance to see if f is continuous or not at x equal 2. Substitute in 2 here. 2 minus 3, we get minus 1. Substitute in 2 here. 2 times 2 is 4, plus 5 is 9. Well, minus 1 is not equal to 9. So right away we see that f of x is not continuous at x equal 2. But again, that is not what you put down on the test. On the test you put down the formal argument. Step 1, f of 2 is equal to, we use this line. Here we have x greater than or equal to 2. F of 2 is equal to 2 times 2 plus 5, 9. So f of 2 exists. How about the limit? Well, does condition 2 hold? Does the limit as x go to 2 exist? Well, because it's piecewise defined, we have to take the limit from the left and the right, because it breaks up at x equal 2. So the limit as x goes to 2 minus of f is equal to, this is the left one, x less than 2, so we say that limit is 2 minus 3, which is minus 1. So the limit from the left exists. All right, how about the limit from the right? Let me do it over here. Okay, well, the limit as x goes to 2 plus of f, that's equal to, now I use this expression, it's equal to 2 times 2 plus 5. It's equal to 9. So we say that the limit as x goes to 2 from the left is not equal to the limit as x approaches 2 from the right. So the conclusion is that the limit as x goes to 2 of f does not exist. Therefore, f not continuous. And since the limit as x goes to 2 of f does not exist, we can also conclude that the discontinuity at x equal 2 is not removable. Not removable. Okay, remember, if f of x let me just mention one thing. In this second example, f of x was continuous at x equal 2, so then it makes no sense to talk about removable, not removable. All right, removable, not removable only applies when you have a discontinuity.